Okay, so let me continue with what we were doing in the previous lecture. So let me quickly recall. We start with the commutative ring R with unit element 1, and we define this prime spectrum, which corresponds to the prime ideals of R being thought of as points of the prime spectrum spec R, and then we define the Zariski topology on the prime spectrum, which comes out of ideals of R. Given an ideal of R, we define a closed subset defined by that ideal. Namely, it consists of all those points in the prime spectrum which correspond to prime ideals which contain the given ideal. Okay, and sets like this form closed sets for a topology called the Zariski topology. They satisfy the conditions, the axioms for closed sets. Okay, and this is called the Zariski topology on the prime spectrum of R. And the formation of the spectrum is actually a functor. It is what is called a contravariant functor. Okay, so it's a contravariant functor from the category of rings, commutative rings with 1. The objects are commutative rings with 1, and the morphisms are ring homomorphisms which take 1 to 1, and it's a contravariant functor from this category to the category of topological spaces. Namely, it associates to every R a spec R, which is a topological space, and to every arrow, every ring homomorphism, it associates an arrow in a continuous map in the reverse direction for the corresponding topological spaces given by this prime spectra. Okay, this reversal of the arrow when you apply the spec is what is meant by its contravariance. Okay, and it's a functor. All right. Of course, if you don't know the definition of a functor, you can always look it up. The idea of a functor is something like a function. It's a generalization of a function. The idea is it has to go from what is called one category to another category, and the category is supposed to consist of objects and morphisms, maps between objects, and of course these maps have to preserve. The objects have some structure, the maps have to preserve this structure. So for example, we are all familiar with so many categories. For example, category of sets is a category for which the objects are sets and the maps are just maps of sets. The morphisms of the category are just maps of sets. We are also familiar with the category of groups, for which the objects are groups and the maps are group homomorphisms. Similarly, you have the category of rings, where the objects are rings and the morphisms of the category or the arrows in the category are ring homomorphisms. Okay, and for example, you can also talk about the category of topological spaces, where the objects are topological spaces and the morphisms are continuous maps between topological spaces. Similarly, you also can talk about category of modules over a ring and so on and so forth. Okay, so the fact is that a functor from one category to another is something that does the following thing. Given an object in the source category, it gives you an object in the target category. Given a morphism in the source category between two objects, it gives you a morphism between the corresponding objects in the target category. And the only thing is that the arrow in the target category may be in the reverse direction. If it is in the reverse direction, it is called a contravariant functor. If it is in the same direction, it is called a covariant functor. Of course, another example of a category is the category of of vector spaces over a field. The objects are all vector spaces over a field, and the maps are the linear maps. That is also a category. So spec is a contravariant functor from the category of rings, commutative rings with 1. The objects are commutative rings with 1, and the morphisms are ring homomorphisms which carry 1 to 1. And from this category, spec is a contravariant functor into the category of topological spaces, namely the category for which the objects are topological spaces and the morphisms or the maps are the continuous maps. So what it does is that to every ring R, commutative ring R with 1, it associates spec R, which is a topological space given the Zariski topology, and to every arrow in the category of rings, namely to every ring homomorphism which takes 1 to 1, it associates a continuous map in the reverse direction of the corresponding topological spaces. So it is a contravariant functor, okay. And the point that I want to recall is that if you take the closed subset Z of I, that itself is a spectrum, and it is actually identified with the spectrum of the quotient of R by I, okay. And if you look at the open subset that corresponds to the complement of the ideal generated by a single element, that also is a spectrum that can be identified with the spectrum of the ring localized at that element, okay. So so roughly the point is that the closed subsets correspond to quotients, okay, and open subsets given by complement of a single function or a single element, the zero locus of a single element, they correspond to localizations by that element, okay. So so the fact is that just like in the usual algebraic geometry, when we first started out, on this side we put we put affine space, and then we put closed subsets of affine space, and then we had a arrow reversing equivalence that went from closed subsets here to radical ideals on this side. On this side we put radical ideals inside the polynomial ring in as many variables as the dimension of the affine space we started with, and there is a similar thing that is going on here. So what you can do is actually put on this side you can just put closed subsets of spec R on this side. On that side you can put ideals. So if you want, I can put ideals of R. So again you have there is a Z map like this which takes any ideal to Z of I, which is a closed subset in spec R, and then there is a map like this which is script I, which takes to any subset T, it takes it to I of T, okay. And what is I of T? I of T is so T is a subset of spec R, so it is a certain collection of points which correspond to certain prime ideals, and I of T will simply be the intersection of all those prime ideals. So I of T will be this will be defined to be equal to the intersection of all those P such that the point corresponding to P is in T, okay. And again you will see that here closed subsets, if you take the set of closed subsets, that corresponds to, there is a bijective correspondence with radical ideals on this side, that is ideals which are equal to their radical, and this will also be arrow reversing, sorry, this will be inclusion reversing, namely larger the ideal, smaller the closed subset, larger the closed subset, smaller the ideal. In particular the ideal that corresponds to the unit ideal, that will give rise to the null set, and the ideal which corresponds to 0 will give you the whole space, okay. And you have statements, there are statements here which correspond to the kind of statements that we got in the case of affine space, okay. So here we got it between closed subsets of an and ideals of the polynomial ring in n variables over k. We have similar statements here. So here also you have, you know, if you have statements like z of I1 is equal to z of I2 if and only if well rad I1 is equal to rad I2, okay. You have a statement like this. Then you have also the statement that z of I of t is just t bar, the closure of the set t, and you also have the Nullstellensatz in its very ring theoretic form, which is I of z of I, script I of z of capital I is rad I. This is the mind you this statement the analogous statement in the case for the affine varieties was a very deep statement. It was a Nullstellensatz, but it is true in this sense for any commutative ring, okay. It is already there, it is God given. So you have this very beautiful thing happening. You start with the commutative ring R with 1, then there is automatically this beautiful picture which on one side translates from ideals to closed subsets, okay. And in fact as I told you it's more this is at the level of R, but if you want to go outside of R and you want to consider other rings gotten from R, like for example you want to consider quotient rings of R and you want to consider localizations of R, then you will end up with going to the closed the quotients of R will correspond to the again closed sets, okay. And the localizations of R by single elements will correspond to the closed the complements, the open subsets given by complements of those closed subsets corresponding to that single element, okay, the ideal generated by the single element. So you get very beautiful you know on this is, you may call this as the geometric side, you can call this as the commutative algebraic side, but the beautiful thing here is that the geometric side has been cooked up from the algebraic side. The space spec R itself has been cooked up from R. I mean there is no in analogy here when you compare it with here, we started with polynomial ring in n variables and that was being thought of as acting on as functions on the affine n space, okay. We already had a space here, but so you had a space namely Kn and you had the polynomials on that space, and using these polynomials you defined the Zariski topology here and you got all these nice correspondences and equivalences, but in this case what you are doing is you are starting with a ring, okay. You are cooking up a space using that ring namely the spectrum, and then you still get this beautiful correspondence with all these properties which are just very very analogous to what you got in this case, okay. So this is at a first point you should therefore feel that you know you should be able to catch the space from the ring of functions, okay. So I will tell you what the arrow what is this max spec, okay. It is very simple. So what you do is that you give me anything on this side, namely you give me a finitely generated K algebra which is an integral domain, okay. For example say this one, something like this. Then of course this is also a commutative ring with 1, alright. Take its spectrum, okay, take spec of this. The spec of this will contain all prime ideals, okay, but what you do is you take a smaller subset, namely you take the max spec. And what is max spec? It is not prime ideals but it is maximal ideals. So you know every maximal ideal is prime and the converse is not true, so you restrict to only the subset of maximal ideals, okay. That will be a subset of the prime spectrum, The maximal spectrum is denoted max spec. It is a subset of the prime spectrum which is given by spec, and since a subset of a topological space automatically gets a induced topology, what will happen is that max spec will also get a topology. It will get a Zariski topology induced from the topology on spec. Okay, the beautiful thing is if you take max spec of this along with that topology, it will be exactly homeomorphic to Z of P. Okay, so in particular what I am saying is if you take max spec of this, you will simply get back affine space up to homeomorphism. See, we have already seen this in the Nullstellan sets. I have already told you that max spec of this is actually Kn, because every point in Kn corresponds to a maximal ideal in the polynomial ring. That is exactly what the Nullstellan set says. So what the Nullstellan set says is that max spec of this as a set is exactly affine space. The point with coordinates lambda I corresponds to the maximal ideal given by xi minus lambda I, with generators xi minus lambda I, right? That is what the Nullstellan set says. But that is just identification of max spec of the polynomial ring in n variables with an, with Kn in fact. It is just a set theoretic identification. But what the claim now is that if you take max spec of this with the Zariski topology induced from spec, then this identification of max spec of k x1 etc xn with Kn will actually be an topological isomorphism, a homeomorphism from affine n space to max spec of k x1 etc xn. So it's not, so the Nullstellan sets is not just a set theoretic bijection, it is a topological isomorphism, it's a homeomorphism. Okay, so in other words, even if I don't have this side, I can get back my affine space by simply taking max spec of polynomial ring in n variables. So that is a beautiful thing. So this whole side I can reconstruct from here by simply applying this max spec, and then it is a matter of exercise to check that this followed by this is the identity and this followed by this is the identity, so that these two are actually inverse associations. Okay, and of course when you check that you will have to worry about isomorphisms, okay, but that can be done. Okay, so so in fact to check that these two are inverses of each other in a rough way you can do that checking now, but then I need to tell you what are the morphisms on this side. So I need to go on and explain morphisms of varieties. Okay, so so let me write that for a finitely generated K algebra K y1 by P, which is an integral domain, we have a homeomorphism max spec K y1 yn mod P to Z of P, which is considered as a closed subset of AN AM. So maybe let me use M here. Let me also put M here. AM. Okay. So the point is that it's a homeomorphism. Okay, and how does one see it? Let me try to explain that. So this is exactly how you go from here to here. Okay, so you know, if I start with Z of P inside AM, where P is a prime ideal in polynomial ring over K with m variables, which is the affine coordinate ring, the ring of functions on AM, the larger space. Okay, then what is the ring of functions on Zp? It is the quotient of the ring of functions on Am modulo p, namely it is this. So that is what you get when you go from here to here, and then when you come back what you will get is max spec of k of y1 etc. ym by p, and what that statement says is that that is exactly Z of p. How is that true? That is very simple. See, what happens is that so what is the proof for this? I will just outline that. So if you want theorem, it is a theorem in its entirety, but it is actually a corollary, because all these are all more and more grandiose versions of the Nullstellensatz, okay, I mean which you get by using after putting all this Zariski topology and so on and so forth and using enough commutative algebra, okay. So these are all various grander and grander versions of the Nullstellensatz. So let me explain this. So you know, this is the Nullstellensatz from Am to max spec k x1 sorry y1 etc. ym. There is a map like this which is given by, you know, give me a point lambda 1 etc. lambda m that corresponds to the ideal y1 minus lambda 1 and so on ym minus lambda m. This is the ideal. This is a maximal ideal in k x1 except k y1 etc. ym, and then I take the point, I put the square bracket to say that I am considering it as a point of the maximal spectrum, okay. So this bijection is simply because of the Nullstellensatz, which tells you that, you know, every ideal of this form is maximal. That is true for any field, and conversely if your field is algebraically closed, every maximal ideal is of this form, that is the Nullstellensatz, okay. Now what you do is you go to the subset which corresponds to Z of p, okay. Just think what are going to be the points here which are going to lie here. Mind you, a point with coordinates lambda 1 through lambda m lies in Z of p if and only if every function in p vanishes at each of those points. That is the definition. You see, what is this? This is Z of y1 minus lambda 1 dot 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 ym minus lambda m. This is what it is. This is just the zero set of this maximal ideal, okay. So, and you know, Z of this is contained in this belongs to Z of p, I mean Z of this is a subset of Z of p if and only if p is inside this maximal ideal, okay. In other words, yeah, if and only if this maximal ideal contains p. That is because you can apply the script I. If you apply script I, okay, to Z of y1 minus lambda 1 etc. ym minus lambda n contained in Z of p, if you apply script I to both sides, you will get I of Z of that, which is just radical of that, which is the same as that maximal ideal, contains I of Z of p, which will be radical of p, which is p, because radical of p is p itself, because p is prime. This is just I am using the Nullstellensatz now. So what this will tell you that is that this point belongs to this if and only if, this is if and only if by the Nullstellensatz the maximal ideal y1 minus lambda 1 etc. ym minus lambda m contains p, okay. And what does this mean? This means that this is in Z of p as far as the Zariski topology on the spectrum is concerned. So it is an element of max spec k of y1 etc. ym mod p. See, what is max? A maximal ideal which contains p, the set of maximal ideals which contain p are precisely the set of maximal ideals in the quotient by p. The set of maximal ideals of a quotient of a ring by an ideal is precisely the set of ideals of the ring which contain that ideal, okay. okay. There is a correspondence between a ring, the ideals in the quotient of a ring by an ideal and the original ring. And what is the correspondence? An ideal in the quotient corresponds to an ideal which contains the kernel, and under this correspondence prime ideals go to prime ideals, maximal ideals go to maximal ideals. It is an inclusion preserving correspondence. So the maximal ideals in K y1 etc ym mod P are precisely the maximal ideals in K y1 etc ym which contain P, okay. So that will tell you that so this will tell you, this will imply the proof, okay. So the so if you want to complete this diagram, what is happening is that here I have max spec of K y1 etc ym, which is identified with am by the Null-Schellensatz, and from this to this there is a quotient map, and there is map in this direction is the max spec of the canonical quotient map. See, there is a canonical quotient map from K y1 etc ym to its quotient by P. If you apply spec to that, you will get, the arrows will get reversed, you will get a map from max spec of the quotient to the max spec of the parent of the quotient, and it is this map which is a closed immersion, namely it is an identification of this with a closed subset of this. What is that closed subset with which this is being identified? That closed subset is this Z of P. That is what it means. This diagram commutes. This is the Null-Schellensatz, and this is also derived from the Null-Schellensatz. So it is actually the Null-Schellensatz for affine space, you restrict it to a closed subset. That is exactly the statement of this theorem. It is simply Null-Schellensatz restricted to a closed subset, nothing more than that, okay. So so that tells you how you get this bijection, okay. Now to make to show that it is a homeomorphism, okay, you will have to show that this is a continuous map in both directions, okay. Now that is something that you can very easily check, okay. So for example, let us show that this map, the identification of due to the Null-Schellensatz, okay. So the homeomorphism I am talking about is this one, okay. Let us first show that this bijective map, which is the Null-Schellensatz, is actually a homeomorphism. Let's show that. That's also pretty easy to see, okay. So let me do that first. So it's very clear that I have this commutative diagram now. I have this commutative diagram, all right, because of what I explained. So you have this bijection, you have this bijection. This bijection is actually coming from here, and this bijection is the Null-Schellensatz. I'll just show that this is a homeomorphism, okay. Once I show this is a homeomorphism, this is a closed subset, this is a closed subset, okay, and it will follow immediately that this is also a homeomorphism, okay. So to show that this is a homeomorphism, that the map, let me write this map am to max spec K of y1 extra ym is a homeomorphism. Let me first show, so I will first show that this arrow is a homeomorphism, okay, then I will show this arrow is a homeomorphism. I will deduce that this arrow is a homeomorphism and I am done, okay. So how do I show something is a homeomorphism? I will just have to show that it is already a bijective map. One way of showing that it is homeomorphism is to show that both the map and its inverse are closed, okay. So the condition for a map to be continuous is that the inverse image of every open set is open, and that is also equally equivalent to requiring that the inverse image of every closed set is closed, okay. And therefore to check that this is a homeomorphism, it's enough to show that this arrow is closed, and it's also, which means that it maps a closed set to a closed set, and to also show that the reverse arrow is also closed because it's already a bijection. Okay, so let me give this some name. Let me use I, and let me call the inverse map in this direction as small z, which is I inverse. Okay, and the reason is why I want to use I is because if you give me a point lambda 1 through lambda m, what I get on this side is actually the ideal of that point, which is y1 minus lambda 1 through y1 minus lambda m, considered as a point of the maximal spectrum, which is a subset of the prime spectrum. Okay, and the map from this direction is give me a maximal ideal. I am just looking at the 0 set for that maximal ideal, which is a single point. The notional sense actually says that the 0 sets of maximal ideals are exactly the single point sets. Okay, so that's the reason for this notation I and z. So it is enough to show that both I and z are closed maps. It's enough to show that they are closed maps. So in other words, what does that mean? It's enough to show that the map is said to be closed if every image of a closed set is closed. Okay, and it's equivalent to even showing that they are open maps, but we always work only with closed sets because that's how the Zariski topology is defined. We specify this in the Zariski topology. The topology is specified by only defining closed sets. Okay, so we always try to do all the checking with respect to closed sets. So you see, so let's start with the closed set here, and let's see what its image there is. So start with a closed set f inside AM. Then you see what is f? F is z of some ideal I, where I inside k y1 etc. ym is an ideal. This is the definition of a closed set in the Zariski topology. Now what is I of f? I of f is, look at this, it is a set of all maximal ideals so let me write that. I of f is just I of x, where x belongs to f by definition. This is the image of a set under a map, and so this will be equal to I of, how does a point so this x in f will have coordinates, so it will be I of lambda 1 etc. lambda m, where lambda 1 through lambda m is a point of f. So this will be, but I of this is supposed to be the maximal ideal corresponding to this point considered as a point of the maximal spectrum, which is a subset of the prime spectrum. So what I will get is I will get the maximal ideal y1 minus lambda 1 and so on ym minus lambda m, such that lambda 1 etc. lambda m belong to f. This is what I will get. Okay, but what is f? What is f? F is by definition f is z of I. We will have to use that, and we will probably apply the Nullstellensatz sums. So lambda 1 through lambda m belongs to f if and only if the singleton point lambda 1 through lambda m is a subset of set f. That is if and only if I can take ideal of a subset. So I of lambda 1 lambda m contains I of f. Okay, because when you apply script I, the inclusion is reversed. But what is I of a point? It is just y1 minus lambda 1 etc. ym minus lambda m, and what is I of f? It is just I of z of capital I, which is rad I. Okay, it's just rad I. So what you're going to get is so the condition becomes if and only if the y1 the ideal y1 minus lambda 1 etc. ym minus lambda m contains rad I. Okay, but you see this is equivalent to saying that this contains I. Okay, because you know because if an ideal contains I, if one ideal contains the other, then the radical of that ideal will contain the radical of the other. Okay, so this is equivalent to saying that y1 minus lambda 1 etc. ym minus lambda m contains I itself. Okay, of course if y1 minus if this ideal contains rad I, it also contains I, because rad I contains I. Conversely, if this contains I, then it will also contain rad I, because you know what is rad I? It's all those elements some power of which is in I. So if some power of an element is in I, then that power of an element is in this, but this is a maximal ideal, so it's prime, so that element has to be in this. So these two are equivalent because the thing on the left side is a maximal ideal which is actually prime, it is a primeness. Okay, so but what does this tell you? But this is if and only if the point corresponding to this y1 minus lambda 1 etc. ym minus lambda m, this the point corresponding to the spectrum is in z of I, because this is how the z of I is defined in the spectrum in the spectrum of the ring. Okay, so in other words, what is this? This is just z of I, and so I of f is z of I, which is a closed subset. So you know I should say it's z of I intersection all the maximal ideals. Okay, which is closed in max spec. Okay, mind you, if I take z of I in the spectrum, it will consist of all those prime ideals which contain I, but I'm looking at only maximal ideals which contain I. So I will get z of I intersection the the max spec, and what I want you to understand is there is a small element of confusion. This z of I is the 0 set of I in, if you want I will put a subscript here, I will put am. Okay, this is 0 set of the ideal I in am, alright, whereas this 0 set of is the 0 set in spec R. So there is a difference between this zi and that zi. Okay, so so let me do that. So this is I need to write that. Let me put sp. So maybe I'll write it a little larger so that you see the difference. So here is, this is z in am k of I, okay, and this is z, I will put z sub r of I, okay, where z sub r of I, this is being considered in spec R, where R is of course k y1 etc. yn. Okay, so there is, and this z is z sub, this is z sub am. So let me correct that as also. Okay, so the 0 sets are being considered in different Zariski topologies. one is the Zariski topology on the affine space, the other is the Zariski topology on this prime spectrum. But the beautiful thing is it's the same ideal. You start with a closed set here that is given by an ideal. It's the same ideal that comes on that side when you take its image. That makes that image of that a closed set. It's the same ideal literally. Okay. So that tells you that I is a closed map. Okay. So this is the reason for that last equality. So this implies that I is a closed map, and in principle one should be able to reverse this whole argument and show that I inverse, which is Z, is also a closed map. So how will you show that? That's also pretty easy. So what you do is conversely let T be a closed set in this, in max spec K y1 through ym. Okay. So what does this implies? T is actually max spec K y1 through ym intersected with a closed subset of the bigger space, which is a spectrum of K y1 through ym. Okay, and closed subset in that is the zero set of an ideal. So it will be Z sub R of some J, where J inside R is an ideal. Okay, and what is this? So what is Z sub R of J? It's all those prime ideals in spec R which contain J. If I intersect with the maximal spectrum, I will get all those maximal ideals in spec R which contain J. So this will be the set of all maximal ideals in this, which by the Nullstellan sets is of the form are of the form x y1 minus lambda 1 ym minus lambda m. These are all those maximal ideals such that the corresponding maximal ideal y1 minus lambda 1 dot 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 ym minus lambda m contains J. Okay, and this is what T is. You can see very clearly that Z of T is just small z of T is Z sub am of J, so it's closed. So let me write that. I have very little space, so let me write it anyway. Then small z of T is just Ez in am of am sub k of J, and which is closed. Okay. So what is Z of T? It's going to be, you know, all those points of am which correspond to maximal ideals which contain J. That means it's going to be all the points of Z of J in affine space. Okay. So Z of T will just be Z of amk of the ideal J. So what this tells you is that the inverse map of I named small I, which is small z, that is also closed. Therefore this is a homeomorphism. Okay. So the moral of the story is therefore that this lower arrow, which is the Nullstellan sets, which says that every maximal ideal corresponds to a point, okay, that identification is actually a homeomorphism of topological spaces. And now it's a matter of routine checking which I want you to do to show that, you know, under this homeomorphism, okay, if you see, you already know that this diagram commutes, okay, you know that this is a subset here, this is a subset there, and you know that this bijection restricts to this bijection. This is a closed set, this is a closed set, okay. A continuous map restricted to a subset will be continuous for that subset with the induced topology. So what it will tell you is that the arrow in this direction will be continuous, okay, and because this is a closed subset here, that's a closed subset there, and similarly the reverse arrow will also be continuous, so that will also tell you that this is also a homeomorphism, so it's not just a bijection. So that will prove the theorem that you have a homeomorphism between z of p and max spec of this, and of course this z of p is z in AM, okay. So moral of the story is that if I start with z of p here in AM, I take its affine coordinate ring, I get this quotient ring. If I again take its max spec, what I get is something that's homeomorphic to z of p, okay. I get back z of p. So it tells you that if I go like this and come back, I get something that is not exactly the same as this, but something that is isomorphic to this. Isomorphic in the sense on this side, at least we have been able to prove that it is a topological isomorphism, but in fact we are going to prove, we are going to define what is meant by a morphism of varieties, and we will show that this map and for that matter this map you can also think of it as a, in the most general sense you can even think of it as a morphism of affine varieties, isomorphism of affine varieties, okay. So the moral of the story is, if I start with z of p, then I go to the affine coordinate ring, then if I come by applying this A, and then if I come back by applying max spec, what I get is not just something that's homeomorphic to z of p, in fact you will get something that's isomorphic to z of p, isomorphic as affine varieties. And what this isomorphism means, it should be an invertible morphism, so I should define what is meant by a morphism of affine varieties, and that's something that I will do. So I am saying that still the picture is not over, that is on this side what we have got in this theorem is just a homeomorphism, but it's not just a homeomorphism, it's even an isomorphism of varieties, okay. And that is the story if you go from here to there and come back, okay. And if you go this way, okay, you will also have to show that I mean the same kind of argument should convince you that if I start with this, okay, and if I take max spec of this, okay, then max spec of this can be identified with this because of literally the same argument, and then if you take the affine coordinate ring of that, I will get something that's isomorphic to this, okay. Only thing is that the yi is, instead of calling the variables as y1 through ym, I might call them as, if you want say t1 to tm or some other names I could give, but in any case I will get exactly a polynomial ring in m variables divided by a prime ideal in that polynomial ring, which will go to this prime ideal under an isomorphism between this polynomial ring in the y's and the other polynomial ring that I am thinking of, okay. So so the point is, if you start from here, go there and come back, what you will get is an object up to isomorphism here, isomorphism varieties. And conversely, if you start with an object here, go there and come back, what you will get here is an isomorphism of rings, okay. So that's what happens, okay. So I'll stop here, and probably in the next lecture we will try to understand what happens for an open set and try to understand how to define morphisms.